once you learn vectors, you can actually extend the idea of vectors and start providing different ways of writing out equations of a line, which is interesting. Now, I'm going to just talk about 2 dimensions in this video. However, the extension typically is used more so for 3 dimensions, because in 2 dimensions, you have studied quite a lot, okay, in terms of grade 9, grade 10, and probably grade 11 and so on, what the equations of a line are. So, as you can see here, I drew a line, and this particular line, so it has the standard kind of y is equal to mx plus b form. And the other one, which is sometimes called the standard form, so which is this one, you may actually see it written out as, 3y minus x, and let's say minus y is equal to 0. And I guess, you might write the x first. So for example, negative x plus 3y minus 1 is equal to 0. So this is typically called the standard equation of a line, which is just ax plus by plus c is equal to 0. And so with these two, so with the y is equal to mx plus b form and this second form, you don't really need anything else in 2 dimensions. And that's why when you were starting off, it was never introduced to you. However, as you study vectors and then you finish off vectors, and then you kind of move over, and then possibly you might be studying lines and planes in 3 dimensions. The 2, y is equal to mx plus b, and then the ax plus by plus c is equal to 0 form, they kind of fall apart for 3D because of the fact that now we do have 3 dimensions. So, what is this concept of a slope in 3 dimensions? Does it even actually kind of work? We can certainly try to define it, but it's not very useful for us. So here I wanted to be able to introduce you to these vectors, and another one from vectors that actually is the parametric equations of a line, so that you can kind of get a gauge of what these are all about. Now, you're going to be running into this, and of course your teachers might present it to you slightly differently, depending on the books you read. You're going to see these items, okay, maybe in a very similar fashion. So this definitely is something that has been introduced in the past. So what is first kind of this vector idea? Well, the vector idea goes from the fact that you want to be able to write out a line instead of in the 2 forms that we had, but in the form of actually representing it, where you can take any point on the line, which is going to be the tip of a vector. And so, as once you have studied vectors, you can actually take a vector, and I'm going to take one, for example, starting from the origin, and let's say, I would point one out, okay, and let's say that it is this particular vector. So we could write this vector as, I guess this is 3, and this is going to be 2. Okay, so that's our vector in the Cartesian form right there. And so that particular vector is going to be pointing to a point, right? And now what we want to be able to do is we want to be able to have a starting point, which might be, let's say, somewhere here. Now, I could have drawn this vector some other place. I mean, I could have just gone over here. It was just convenient for me to do that 3, 2 spot, but I could have done it in any other spot. So it's kind of your starting point. And these vectors, okay, when we're trying to represent these particular lines, sometimes they're referred to just simply as a ray, right? So you can imagine kind of like a ray of light even. So that typically will have, some kind of a notation as R for the ray. And this would be my, kind of initial, that initial one. So sometimes it's subscripted as I, or maybe as O, or 0, right? Which is your initial vector, okay, or initial ray, which is trying to describe this particular line. Now, with this vector, it obviously does not describe the whole line. It just actually points to one particular point, which is the point 3, 2, which is at the tip there. So now how would you actually express it in terms of trying to capture the entire line? Well, the way that, mathematicians of the past have done it is in the following way. So they basically said, okay, well, you can start off with something like this, and then you can take, your old school kind of vector, which is going to be parallel to this line, right? So you can take a parallel vector, which is going to be to this particular line. Now, that particular vector, I am going to refer to this, but now again, it's not just, me, this has been done in the past. So this is going to be a vector, and I guess because of the vectors, I'll put this little notation in there. And this notation is going to be a vector which is going to be parallel to the actual line. Now, how do I find a parallel vector? Well, I mean, if I have 2 points, right, on the actual line, I can make vectors out of those 2 points, and I can subtract them, and then that is going to give me a vector which is actually on that line. So that is something that you've learned with vectors. Now, another way is, of course, you can look at your rise over run, and you can know exactly what that vector would be, right? So if you recall, and this is, I guess, one of the reasons why we sometimes refer to this as M, or mathematicians have, and that particular result, what it is that M is just simply coming from the rise over run. And in this case, I guess my rise is 1 and my run is 3. And I also can see that from right here because that's the equation that I started with. And for this, you can take your values. So since it's rise over run, really, if you remember rise over run, which is the change of your y over the change in x. So here is your numerator is going to be your y value, and your denominator is going to be your x value. So right here, one particular choice, okay, of a vector would be this 3, 1 vector, and that would be parallel to that line. So, if I drew out this vector here, it would have been basically this one, because it runs for 3 and then rises for 1. And now, if you take the combination of these 2 vectors, right? So if you add them together, it's going to give you a result which is on the line, right? So for this particular line, I mean, if I extend it all the way through, let's say somewhere over here, and then I'm going to change the color, okay, of this, let's say make it purple. And for this particular item, so if I add up the 2 vectors, and I'm referring to the one vector which is touching the line, and now this is the second vector which has the same, kind of, it's parallel to my line. Let me duplicate this. So, if you notice that now all of a sudden, I've created this resultant vector in here. So that resultant vector is going to be, let me, do a dotted line in here. So this is my resultant vector, which now points to another point on the line. And what we like to do, okay, or at least what mathematicians like to do, is they like to take this and then they will say, is that, okay, well, you can add these together and now you can scale that vector, so the parallel vector, as much as you like, right? The initial vector which touches the line is not going to change. But if you now scale the vector itself, right, so that M vector, and you scale it, either make it bigger or smaller, then what you're going to be doing is you're going to be finding all the points on this particular line, right? So that's what's going to happen. And we actually, in terms of the mathematicians, what they said that, okay, so that's neat. So I can actually define my line by creating a vector which will touch every point on the actual line by having a starting point, so a starting vector. So doesn't matter which one it is, as long as it's touching somewhere on the line. And I can add now some scaled version, right? So we typically scaled by k in here. So this is going to be k, this is 3, 1. Now, technically, you'll see it in textbooks and other mathematicians who have done this work. you'll see that simply this is going to be just a t, okay, typically that we put in here. And sometimes the t actually is just a parameter that we have. And very often it might actually refer to time, although it's not necessarily in this case. So this particular t is just some number, so it belongs to r. And if we scale it, so depending, so if it's 0, for instance, then we're back to just the vector r0, so that first initial vector. But if we scale it and we make it, let's say 1, right, then it's going to get back to this. And then if we scale it and make it something else, or something smaller, right, it's going to be now, something less. And if we make it bigger, it's going to take a different point. But as you can imagine, it basically just tracks and just moves this, okay, around. And if it's negative, right, so if that becomes now negative, then what we will have is it's going to be this particular vector that we have right there. And if I take a scaled version of this and make it negative, so what that would mean, that is that it would be the opposite vector, right? So this thing would actually go and flip around. And if it's negative, right, I mean, it's going to be scaling itself. Now, if it's a very small negative, then it's going to be, much, much smaller in here. And you can now take this, right, and then attach it right here. And then you will notice that what's going to happen, it's going to be giving you another point, right, now in the opposite direction. So if it was positive, it's going to give you all of these points from 0 onwards on the line. If it's 0, it's going to give you that starting point. And if it's negative, and I'm referring to the t, or the k, the constant, it's going to just traverse it, okay, on the left-hand side. Now, I've actually created this on decimals just to show you how it traverses, right, every single point on this line. And it's actually another way. This is called the vector representation, okay, of an equation of a line. So what it does is it has an initial, right, vector which touches the line, and then it has an addition of a scaled version of a vector which is parallel to the line, and it just gets scaled up and down, and it just moves these things around. So it's really cool. So here I have done this. So notice that right here we're starting at t. If you look at the left hand side, it's 0. And basically, instead of the arrow, I just put there's a dot in decimals. And that is the point on the line. And this is the actual line, which is 1/3 x plus 1. And now as you scale this, right, as it goes positive and negative, so if I let this play, okay, you notice that now it's being negative. It is actually, this is the resultant vector. So that's what you see here. So this is the resultant vector, and it is moving around, right? So now I actually make it so that it reverses back, so that it's just now traverses this line, and you can get any point on the line within here. So this just actually plots it for you. And what you see in the purple is the actual vector, the resultant vector of the addition of the initial one plus the scaled version of the parallel one. And this is really neat. You can take the t, and of course, if you make it go to positive, meaning it takes on all real numbers, then, it can traverse the entire line. So that's another way of being able to do a line, except here you are using a vector kind of notation for the line. Now, of course, you might say, well, why am I going to be doing this? It's so much easier just to do y is equal to mx plus b. I agree with you, for sure. It's way, way easier just to put, and y-intercept, and then do a slope, connect two lines, and just draw a line through it, and you're done. That's certainly true, but you have to remember that with the vectors, the idea is more so for 3 dimensions, because in 3 dimensions, if you draw a line, it may not be in the xy plane. It could be, all anywhere. And if you want to be able to properly try to see how that line is, in terms of some algebra, okay, then this is one way to do it. So in general, what we do is we basically take a vector. So now these are the rays. This is what the mathematicians use. So they'll use, a ray, which is equal to and this is going to be r. Okay, this is your starting point vector, which touches the line, okay, plus the t, which is just traversing the actual line, and then you have your slope, which is m. That's what typically is utilized, and you might see this in textbooks, and other teachers might use it. So this is definitely not, in terms of my invention or anything like that. So this is one particular way of expressing, or it's actually the third way of expressing a line that we would have. And, once again, if you wanted to recall, so if this is your line, and you have your axes, right, which might be set somewhere. So this is, let's say, your axes like so. Let's make it a little bit different than the other one. Let's say that was it. So you first will try to find one particular vector which is going to touch. So that's, doesn't matter which way it is. It could be, even in this. So let's say that's your r, okay, 0. This is going to just touch it. So that's your r0 vector. And then you need another vector, and this is going to be the vector which is parallel to this. It does not matter if that vector is going to be parallel in terms of, going in this direction, right? So it certainly can be that. So so this is your m vector. So it's either can be parallel in this way, or, if you take this one, you can, whoops, I don't want to definitely switch it back. So let me put it back in here. It can be also in the opposite direction. So, it can be in this direction. So it would have been looking like this. And then if you swapped it, it would have been this way. So it's not going to be unique, by the way, because of the fact that this vector can be any arbitrary vector which just touches the line. So that's not unique. And then, this also can be not unique as well, because it's going to be either, in this case, moving to the right or moving to the left, up or down, depending on what the slope is. But it can also be scaled, right? It can be a big vector, smaller vector. You might want to have it as a unit vector, and that's fine. But that's up to you. And then this, okay, just simply will traverse the line for you, as you saw they're done on decimals. All right, so this is one way of being able to do that. Now, in the title, I have labeled this, and I said, that it's vector and parametric equations. So there's actually a fourth way of being able to write these out. Now, fortunately, okay, once you are familiar with this representation, then doing the parametric one is actually not that difficult, okay, to be able to do that. And the way that we do that, so let's say, this is going to be our line, let's call this line 1. So the way that mathematicians do this is they do the following. So they'll say L1, okay, is the equation of the line that you have. And this will, again, depend on who's writing it, who the teacher is. But what you would see within here is something like this, where you have done this, and this is, let's say your line 1, and it's going to be broken down. You're going to break down. The parameter is going to be your t, and you're going to break it down in terms of its x and its y components. So again, this will just depend where you're seeing this. I sometimes do like to put it almost like it's looking like a function, right? So where it's x dependent on t, and that's going to be your parameters of your x. So that's, let's say for this one, it would have been 3 plus, and then the t times the 3, so it's going to be 3t. And this will give you every value, depending on what t is, to try to find your x. And then the corresponding one, so this would have been your y. And for your y, what you will have is, so this is going to be 2, and it's still a plus, I guess, and this is going to be 1 times t, so that's just t. So that is your parameter again that you see there. And you can say that t is an element of the real number line. And this would be another way. So this is called the parametric equation, at least that's what the mathematicians call this. And that's what you would have. So you have basically 4 different ways to be able to express this. Now let's do an example kind of from scratch to be able to see this. And then let's build out all the 4 different ways of representing a line. All right, and the way that I have kind of presented, or at least the example that I'm going to work with you, is this one. So we have 2 points. So here's point 1, and then here's point 2. And then what we will want to do, maybe what I'll do is I'll just move this out of the way for the moment, put it on the next page so it doesn't trouble us in here. So we have 2 points. So let's try to see. All right, well, I hope that you still remember, all right, so how to do this in the old school way. So if we had and wanted y is equal to mx plus b, then, well, we certainly need our slope. So our slope is the change. So I'm going to say this is my point 2, this is going to be my point 1. So I'm going to take, so it's going to be 5, minus 2. So that's your y2 minus y1. So that's going to be your rise, and then over your run, which is going to be your 4 minus, this is negative 1. So that's going to give us 3. This is going to be over, and this is going to be 5. So that's our slope. So y is equal to 3 over 5x plus our b. Now, how can we find our b? Of course, we can substitute any of the points on the line. You can pick any of them. I'll pick this one. So if I substitute that back in, I will get 2 is equal to 3 over 5. And this is negative 1 plus b. So now I can solve for b. It's going to be 2. The negative will come in front, and then I'm going to shift this whole thing over on the left-hand side. That's going to be plus 3 over 5. And this is b. Now finding a common denominator, so 10 over 5. And this is going to be 13 over 5, which is equal to b. So here's our equation. Y is equal to 13 over 5. Sorry, 13 over 5 is the y-intercept. So that is 3 over 5. X and plus 13 over 5. So that's one way. Now, if you want to find kind of this equation in standard form, we got to shift everything back over, okay, to the left-hand side. So in standard form, this would be, if I shift it over, I'm going to get negative 3 over 5x plus y minus 13 over 5 is equal to 0. Now I'm going to get rid of, this will be fine. Typically, we don't like the denominator in this form. So I can multiply by 5. I'm going to multiply by negative 5 because I don't want that negative in front there, as you see there. So if I do that to both sides, left-hand side and right-hand side, so what I'll get is, this is going to be just 3x. This is going to be negative 5y. And this is going to be positive 13 equals 0. And this is now a much nicer standard form than I had right above. So that's going to be my second way. Those are the 2 common ways that you actually do it. I love the y is equal to mx plus b. Personally, that's one of my favorite ways to express lines. So now, if I wanted to express, and I'm going to do this right from the 2 points instead of, taking the actual slope. So I'm going to copy this. And let's say somebody asks you to find the actual vector equation of a line, in this case in 2 dimensions. So, how would you do that? So the way that you do it, because these are just 2 points, we do need vectors, correct? So I will transform these. So these, instead of being points, I'm going to treat them as vectors. So now I have 2 vectors in here. So those are the 2 vectors that I have. So these are the points and these are the vectors, at least in Cartesian format. Now what I will do is to find my, first, so, recall what I need. I need an initial vector which touches the line, plus I need a vector which is parallel to the line. So first of all, the first one is easy. You can pick any of this. You can pick this vector to be r0, or you can pick this vector to be r0, or any other point or vector which touches the line. It does not matter. So I'm going to pick, let's say the second one. So this is going to be 4, 5. So far this is what I have. This t, I know this is going to be an element of the real number line. And now my m, so what is this m going to be? Well, the easiest way to do that, so if you recall, if you have two vectors, right? So as they're kind of going through, so in order, so if you have, I'm not saying that these are going to be, let me just guess, so -1 and 2. So this one is kind of going to look like this, and then 4 and 5. So that one is going to be, something like this, except it's going to be much bigger than this. I just don't want to write over it. But they're going to look something like this. So if you want to find, your vector, so here, right there, so don't forget that you can find that vector, which is going to be your parallel vector. So this m vector is nothing else but simply, so take, if I'm going to say that this is my vector 2, this is my vector 1, so I can take these vectors and I can subtract them. So v2 minus v1, and it's going to give me the actual vector which is parallel to the line. Now I'm going to just calculate this, and then you'll see, and you can do it visually for yourself, because this is exactly what's happening. And don't forget, if this point is on the line and this point is on the line, so as you can see there, if you do the subtraction of the two vectors, then you're just getting the resultant vector. Now it depends if you do v2 minus v1 or v1 minus v2. It doesn't matter, because you just want a vector which is parallel. Clearly, that's going to be parallel to the line, because that line would be, going right through those 2 points. And you're just finding the subtraction of the two vectors. So that is easy for us to do. So within here, so let's say this is going to be 4, 5, and minus -1, 2. So what does this give me? 4 minus, I guess that's a positive, so it's going to be 5. And then 5 minus 2, which is 3. So notice this is going to be 5, 3. And don't forget, so this is your x value and your y value. And if you think back of how we started in here, well, the x and y, so that's just rise over run, right? Rise over run. And what is that? Well, that's 3 over 5. But wait a minute. Yeah, that seems correct. Notice if I go back in here, this indeed, right there is my slope. And that's exactly what you should get within here. So when you subtract those two vectors. So now we have found right there our vector equation of the line. So that is at least one example of it. And there's, there can be many others as well, of course, depending on what you choose for your initial ray of your vector, and then which one you choose for your kind of parallel vector to the line. Now, if you want to write this out in terms of its parametric equation, well, that's not a big problem in here. So within here, so my parametric equation, so for this particular line, what would it be? Well, so this line is, well, my x. You can put the t, you don't necessarily have to. That's going to be my y. And, so for t, r, so we kind of do have to write that if we're going to use t, or whatever variable, whatever variable you use, or your parameter t or parameter k, right? So this is the parameter. It's kind of like going back to functions again. And now within here, so we would start, so we're going to say, okay, so for my x, it's 4 plus 5t, and for my y, it's 5 plus 3t. And that's your parametric equation of the line. That's all that you would have right there. So now lastly, so I have this interesting point. We knew how to check if a point is on the line, right? If we have y is equal to mx plus b, or if we have ax plus by plus c is equal to 0, if we have this, then we can just substitute and we'll know exactly, right? As long as we get left-hand side equals right-hand side. But how would you check it, using either the vector equation of the line or the parametric equation of the line? Now here it's asking us, or at least I'm asking you, okay, check using parametric equation. So what you must do, so don't forget, this is your x value and your y value for your point, right? So whatever point this is. And what you can do is you can just take this. So you can literally just take this. So I'm going to copy it. And you can substitute within here. So if I take the first one, so this one right there, so my 124 equals 4 plus 5t. I can now solve for t. So now solving this for t, if I bring this over to the other side, that's 120, and then equals to 5t. So now divide by 5, so 120 divided by 5 equals to t right there. And we can certainly do that. I guess that's going to be 4. So 24 is equal to t. Now, once you have this, right, how do you, do you know is this on the line or not? What you need to do is you can do, you can also take this and substitute it back in here. So what you would get is 145 is equal to 5 plus 3t. And now you can solve this for t, and you want to see 24 here. You want these to be the same. And if they are the same, then it is on the line because it has the same parameter. If they're not the same, then this point is not on the line. Now, what I like to do sometimes is, because I already have this, then instead of plugging in, so instead of plugging in this, right, into here, then what I do is I'll just, since I've solved for this already, I just plug it into here and just check if I get the same value. So what I mean by that is, let's plug in 24 into this. I'm going to get 5 plus 3 times 24, right, within here equals 5 plus 3 times 24, what is that, 72, I guess. And that's going to be 77. And 77 with this parameter clearly doesn't give me 145. And so what that would mean is this is not on the line. If you did the same thing here, right, and you solved this all the way through, so sure, you can bring this over. You're going to get 145 minus 5, so 140. Now you're going to have 3t, so divide by 3 on both sides. So you're going to get t is equal to 140 over 3 right there. And you know what, I don't want to be doing this in my head anymore. 140 divided by 3, so which is 46 point something, right? So 46, it looks like 2/3, which is clearly not 24. So again, it's just showing us that it does not work. All right, so with this, I hope that you get a chance to see and get a little bit of intuition in these two new ways of being able to define an equation of a line, either through vectors or a parametric equation. And that's what you will have. And with these tools, you can then move on to try to do the same for lines in 3 dimensions. And I'll do that video as well, put a link up above there, okay, to it if you want to see the 3D. All right, so thanks for watching. I hope that you found this useful. Happy studying.